Welcome to June 25th's LeetCode Challenge, Redundant Connection. In this problem, a tree is an undirected graph that's connected and has no cycles. You are given a graph that starts as a tree with n nodes, labeled from 1 to n, with one additional edge added. The added edge has two different vertices chosen from 1 to n, and was not an edge already existed. The graph represents an array of edges of length n, where the edges at I is the connection between node A and B, which indicates that an edge between node A and B in the graph. Return an edge that can be removed so that the resulting graph is a tree of n nodes. If there are multiple answers, return the answer that occurs the last input. So we see here we're given an array of edges here, and there's one additional edge added such that it makes this a cyclic graph, but it's not. It's supposed to be an undirected connected graph that has no cycle. So there's one edge in here that makes this cyclic, and it's the last one here. So let's go through this. So we have an edge. So 1 connected to 2, 1 connected to 3, and 2 connected to 3. You see how this last one, 3 connected to 2 connected to 3, makes it a cyclic graph. So you want to remove that. So it'll be 3, 2. That's the node that is the edge that you're removing. So return an edge that can be removed. Let's go for example number 2 here. So we see an array of edges here. We have 1 connected to 2, 2 to 3, 3 to 4, 1 to 4. This makes it cyclic. Then we have 1 to 5. So notice how adding node edges 1 to 4 will make this cyclic, and you want to remove that edge 1 to 4, or 1, 1, 4. So how do you go about solving this? So for this, I think using if we go bare bones basic, we'll go back to our graph theory algorithm where we do a depth first search. So what we're going to do is for each graph, say A, B, we're going to do is we're going to traverse through a graph using a depth first search to see if we can connect nodes A to node B. If we can, then there must be a duplicate edge within our graph. So let's kind of walk through that together. So we'll walk through each element of our edges, and we're going to start off at the singleton nodes. So to start off, we're going to create a graph containing all our nodes in the graph. So graph equals I'm going to use a default dict. So it's going to contain all of our nodes within our graph. So what we want to do is walk through the edges and build our graph the first time. And then we're going to walk through, and then we're going to do a depth first search to see if there is a connection between node A and B. That's a duplicate, or redundant, I should say. So let's start off with just continue our algorithm. So let's see, for edges A and B in edges, for nodes A and B in edges, we're going to create a set here that's called visited. So we've visited before or seen it before. And it's going to be empty for now, but we're going to add some things to it for our depth first search. So if A is in our graph, so node A is in our graph, and node B is in our graph, and we're going to define a function called depth first search, which takes in node A and B, and it's going to tell us whether we have whether A and B are connected or not. So if they are, return node A and B, and this is the answer we're looking for if there's any redundancy. And then obviously, if this is not true, then we want to do is connect A to B if they are making an edge together. So within our graph, we're going to take we're going to take index A and connect that to B, and likewise connect B to A because it is undirected, so we have to add it A. So we have the general skeleton going on. Now we need to define our def first search. So define def DSF, which takes in so the source is where we are. So and we want to connect that with an edge to a target node. And this is going to return a Boolean. I'll just make it Boolean. So if our source node, the node that we're starting on, is not in visited, then we're going to add it to our visited list because we are visiting it. Dot add source. If the source node is equal to our target, that means that the target node is the source node, then we're going to return false. Return true. True. That means that we have already seen the source and the target connected to each other. And then what do we want to do next? So return true. Next, that first search is to try to figure out whether there's any connection between A and our source and our target. So what we're going to do is we're going to do this return. We're going to make a set here. So here's a new function I learned lately, any. So this returns true within any parameters inside. That's a Boolean that's going to return true. So I think that's true for our depth first search. So instead of, so we have a depth first search takes in two parameters here, our source where we are and our target. So what we're going to do is go to the neighbor of the source. Let's call it neighbor. Spell it that way. And target. So we're going to do it for neighbor in our graph at the source. So we want to know whether, so the source is not connected. If it is, return true. If it's not, then we want to return if there's any of the source's neighbors connected to the target, right? For each neighbor in the graph of the the graph related to the source. So let's run this. Done. Okay, accepted. So essentially what we did was we created a graph which connects, stores all of our nodes. Then what we did was we defined a depth first search algorithm that searches whether we have the source we're on, so the is connected to the target or not. So if the source is not in the visited, we're added to the visited set. So if the source is equal to the target, then return true because we are on the source that's already connected to the target. If not, we're going to return any true element when we do the search again towards the neighbor of the source. So if the source is not connected, we're going to check this neighbor, see if it's connected to the target. If yes, return true. Now for each nodes A and B in the edge set, we're going to have a visited set. And then if A, we're going to reset the visited set, I should say. So if A is in the graph and B is in the graph, and our depth first search returns true, return the nodes that are connected together that are redundant. If not, then what we're going to do is add graph A, node A to graph node B, and node B to node A. So this is a time complexity of n squared, where n is the number of vertices, so the number of nodes, I should say, and also the number of edges, I should say. So the worst case for every edge we include, because we have to search through each previously occurring edge of the graph. So we would do it once to make the graph, and then again to see if they're connected. So it's n squared at worst. O big N squared, I should say. And space complexity is big O of n, because we just make the graph once with n amount of nodes. So yeah, that's pretty much it. Have yourself a nice day.